If you can bring up my slides as well. Slides? Okay. Hello, everyone. Welcome back from lunch. My name is Mathias Rönnblom. I work at Ericsson, and I'm going to talk about some improvements in pseudo-random number generation that we've been doing in DPDK. So here's the agenda. I'm going to start to give you an introduction, some use cases in a DPDK context for random numbers, the DPDK API, the old implementation, so prior to 1908, the goals I set for the improvements I did for 1908, and then I'm going to talk about the implementation, say a few words about seeding, and then if there's time, I'm also going to talk about bounded random number generation. So what's a PRNG? Well, I'm sure you all know. It's an algorithm for generating a sequence of numbers that looks random, but are not. They are deterministic, and the sequence is set by the initial state of the generator. So that's what's called a seed. Random numbers are fairly common in network stack implementations. Maybe not in the fast path, but for things like TCP backoff, for example, port allocation, things like that. They're also, at least in my experience, very common when you do functional performance testing of networking stack, because usually you want the data or the traffic patterns to be random. And some of the aspects of the algorithm and its implementation, it should have good statistical properties, so be uniform. Well, in this case, to adhere to the distribution specified. So in this case, in DPDK, it's uniform distribution, so every number should have the same probability of showing up. There's also a bunch of different tests you can apply to the numbers to see if they look random in a more formal manner. There's also the question of thread safety, efficiency, and security is often a concern. It's not a concern for DPDK because the DPDK PRNG does not address the case of using it for security reasons. Maybe you could, but I don't know if it's a good idea. So here's the API, very simple. You have a function that generates a random number, 64-bit, and you have a function to seed what looks like one generator. So you will also have automatic seeding at this application startup, or at DPDK startup rather. But this provides an opportunity for the user to specify a seed. Maybe you want to have a random sequence, but you want it to be deterministic, so you can rerun the same test case, for example, and get some predictability. So how did things look prior to 1908? Well, the RT random was just two very simple static inline functions in the header file, and they were using lrun48 and srun48 for the seeding. So that's have been in Unix for ages. It has a uniform distribution, and the range is 31 bits. It is not thread safe, and I filed that as a bug. You can argue it's not a bug, but the API was kind of not specifying whether or not the RT rand was supposed to be thread safe. I thought it would be a good idea. And it's implemented with what's called a linear congruential generator, which is basically it's a fancy word for you take the model operation with a magic number, and then you add the magic number, and then you have the new number, which is also the new seed, so the state of the generator. Very simple. And RT-RAND used two of these calls, and those of you that can add integers understand that 62-bit is less than 64, so the two of the bits are always 0. And this, even I can understand, this is not a good property when you try to achieve something that looks random. So my initial goal was not very ambitious. I basically just wanted to address the thread safety issue, because that was the issue that was pressing my work. And I also wanted to not change the API, preferably. Then I started to look around for thread-safe variants of LRAN, for example. And then I came to realize, with some help of Stephen Hemminger, that LCGs were not the state of the art. Maybe in the 70s, not now. So I wanted to address the higher quality numbers, especially the 2 bits that are always 0, but also generally have better statistical properties. It would be nice to have better performance, better API documentation, improve the seeding, and also have some test cases that prove that the performance will actually, well, it didn't necessarily have to be better, but still good. Actually, the performance, even though you don't care about correctness, which you probably should do, but if you don't, the LRAN has the problem of the shared state also being a performance bottleneck. So if you do like a traffic generator and use LRAN a lot, the cache line is going to bounce around in the system. Yeah, and also the question of bounded PRNG generation. So there were a couple of things I didn't do. Actually, a couple of these things I started doing, and then I came to the conclusion that I had a good idea. I did a 32-bit version of the random function because I realized that usually 32 bits enough. But then it turned out that, yeah, it was faster, but not by a whole lot, so why bother? It's better to keep things simple. You could also consider having multiple distributions, like, for example, if you look how C++ does things, it's very configurable, both in terms of configurable distribution and support for a whole range of different algorithms. But I kept things simple in DPDK, so, and if you want the really fancy stuff, you can go to an external library. That was my reasoning. So the general design is that, as I mentioned, I kept the API. I managed to keep the API the same, and I don't follow the common pattern of the user supplying the state of the generator, which is common, for example, in libc. Rather, I follow the DPDK design pattern of having per core data structures. So it's a data structure that's indexed by the L-core ID. So this approach makes it thread safe for use by L-core threads, not generally thread safe, but for L-core workers. The seeding is still unsafe because I figured this would be used during application initialization, and typically you single thread at that point, so I didn't bother to make that safe. You can certainly do that if you want to, but I didn't. And the seed is huge. The L-core seed is the seed that application gives or that's generated at startup, plus the L-core ID, because you want to use different seed on the different generators. Otherwise, you'll have the same sequence on all the cores, and that would be really silly. And I also, in the process, I also removed this static inline. I think static inline is actually overused in DPDK by a large degree to have them inline, and then there was no reason for having that. So that's actually a change. Technically, it's a change or extension of the ABI, but it's both ABI and source level compatible. So I hope it doesn't break anything. So this is the generator I ended up implementing. It's something called a Tausworthe, I don't know, generator. It's a DPDK native implementation, so doesn't rely on any third party or libc or anything like that. Well, technically, it's a maximally equidistributed combined Tausworthe generator. So combined meaning that there are actually 5 sequences that you combine to one as the part of processing. So the code is much larger than an LCG, but it's actually more performant because the instructions are simple. And not being an expert in this field, I took something that's well known, well analyzed. I send you, there's a link included to the paper. And then, yeah, the generator natively produces a 64-bit number, so there's no combining high and low bits like in the old implementation. And you have one of these instance of these struct per core, and you need to seed them according to the rules of the algorithm. And what comes in from the application is just a single number. So I use an LCG to seed the Tausworthe generator. So since I was messing around in the area of random numbers, I also took a look at seeding with some help of Bruce. So originally, and prior to 1908, you just used RTC or the equivalent on other hardware platforms. Now we use kernel service if available. It's a compile time check. If it's available in libc and available in the kernel, we use get entropy, which is way better than just using the TC for seeding. If it's not available, we use the x86 instruction if we're running on Broadwell or later. And then as a second fallback, we use the old approach, or just taking the wall time, basically, to seed the generators. So I have some performance numbers, a bit of a performance freak. So the first one is the original implementation in its static inline form. So this is an RT RAN call. It's not an LRAN call. Actually, 2 LRAN calls. And this is running on single core. So if you're using this for multiple cores, it's going to look way worse. It can be really crazy bad. But this is single core performance. And since I started out with LRAN 48R, I also have those numbers. So it's a bit slower. I mean, this is all acceptable. Very few applications spend all their time on random numbers. But still we're since I was messing around with this, I try to make it good. And then we have the native Tausworthe generator for 19 cycles. And just for comparison, this is not really a fair comparison because the C++ framework is much more elaborate. I also took what seemed to be the default generator in C++ 11. So we're beating C++, but it's not really on equal terms. So I think I have time to say a few words about bounded PRNG. So usually you don't want the full 64-bit. You have some upper bound for your random number. And this is a very common pattern that you just do a modular operation, and then you're good to go. And to be fair, it's a pretty good approach. If you have constant power of 2, it's really fast, and it produces a uniform number. If you have a constant but not a power of 2, then it's still pretty fast because the compiler can do, I think it's called strength reduction, so you don't have a div instruction. So it's fast, not quite as fast, but still fast. But your uniformity will hurt. So some numbers will be more likely to show up than others. And the worst case for that is that some numbers are twice as probable to occur. But yeah, So, and this sounds like a pretty heavy bias, but it only happens when the numbers are close to the maximum range of the generator, or maximum, the upper bound of the generator. So 64 bits in this case. So I think it's you can still do model operation, and I won't complain. But if you really care about your random numbers, you can use RT random max, which is a new function in the DPDK random API, and it produces an unbiased number. Basically, what it does is just it creates a bit mask, and then if numbers too great, it's a part of 2, of course, a bit mask, and then if the number is too great, then it would just redo and create a new number, which has some side effects. So this is the cost of using the bounded random number generation. As you can see, constant is cheap. If you have a variable upper bound, so a runtime variable, then it's gonna go up, and this is because the div instruction, which I mentioned. And then we have RT run max, the best case, which is, pretty cheap. And then we have the worst case average. And this is the average for the worst case. If you have the worst case is infinity. There's no upper bound on the execution. So and that can cause some discomfort if you have trying to meet some kind of a latency requirement. But it's very unlikely it's gonna execute for very long. You're very unlikely to miss. Like if you have a 10 microsecond deadline, you're gonna be fine. The system is more likely to be hit by an asteroid than missing that. But that might happen actually. That's all I had. Any questions?
Entropy generation. How did you establish what entropy source was best?
Yeah, so you said that one of the calls, the get entropy call, was best, right? Giving you the best results. How did you establish that? Do you generate a massive histogram or something like that?
No, I didn't analyze it. I just took for granted that kernel guys knows what they're doing, and also that maybe you don't want to rely on hardware. I mean, this is not security sensitive, but nevertheless, it was easiest. And it's also portable to the extent it's available in the kernel.
Gotcha.
So I'm not saying that get entropy is a lot better than RDC.
That's what my real question was.
I find it likely that's the case, but okay. I haven't proved it. Any more questions? Okay. Oh.